In this slab I have a shaft with a cam on that shaft rotating, and as it rotates, these followers both above and below the cam follow the cam, and we see that there are 4 of these shafts. And so then on the back side of these shafts is a roller which keeps the shaft centered inside of this component. So let's watch this play. So we see that these shafts move up and down. So that was 1 second of motion, 150 RPMs. I'm graphing the velocity of one of the shafts, and we see that it moves in one direction, it dwells for a period of time, and then moves in the opposite direction. And of course, the shaft opposite of that does the opposite motion, and then the other 2 shafts are 90 degrees in time with the first shaft. Let's slow this down a little bit, and I'll play it again. So we see the cam is rotating, this shaft is lifting, this one is dwelling, this one is dropping, and this one is dwelling. Now this one is dwelling, this one is lifting, this one is dropping, this one is in dwell. So it dwells for 120 degrees, the lift or fall is for 60 degrees. Harmonic motion. And of course, we're watching this slow down considerably. It's actually 1 second of motion that we're watching. If I turn on the display of the velocity of the other shafts, so I think you get the idea of the motion. I'm going to stop this. I'll rotate this around so that you can see it from more angles. So each one of these 4 positions, I have a shaft with a roller on either side of this cylindrical cam, and then this shaft is free to move up and down as these rollers follow the cam, and then this roller keeps the shaft centered. And so we see 4 of those. We see the rise, the dwell, and the fall. So let's look at how to set all of this up. So first thing I did was start a new metric assembly file, and I gave it the name push-pull cylindrical cam. And then I'm going to go to the design tab, and underneath this cam I will select a cylindrical cam. Now if we do a preview of this, we see that the cylindrical cam does a slot. So we're going to have to be clever with this, where we're going to move this bottom of the slot up and the top of the slot down, because the bottom of this roller, we need for a roller up here to follow this face up here, and then a top of a roller here to follow this face down here. So we're going to have 2 rollers here instead of just 1 roller. And let's look at how to set this up then. So for the radius of my cam, I'm going to use in parentheses 256 plus 27. The 27 is the width of my land on the cam, and divided by 2. So that's the radius. For the groove depth, let's do 27. For the roller radius of our cam, when we design a cam, the size of the roller and the position of the roller affects the shape of the cam. So we need to make sure we have the right size roller. In this case, the diameter is 35, so radius 35 divided by 2. If we were going to have that eccentric offset, we would put in eccentric offset and angle. In this case, our roller is going to be straight along the axis of the cam, and then for the roller width as 27. Let me delete this graph and we'll put it in again so that you can see how to do this. So initially your graph is going to come up looking like something, and I'm going to turn everything off except for the first graph, which is the lift or displacement. I've expanded this dialog box and I'm going to tell it to do 720 calculations, or 720 points on the cam, or every half of a degree, and I'm going to model 720 points. So the calculations occur here on the calculation tab, and then the model is when we actually create that. I'm going to tell it first I'm going to do the lower, so we have to do the one side and then the other side. If we were doing the slot as in this image, then we could do both at the same time, but in this case we have to do these separately. Now there are some tricks that you could use to do them both at the same time, and I thought about showing that method, but I just decided that was just one or two, maybe 5 tricks too many, so I'm just going to do it step by step with one at a time. Our follower shape will be cylindrical, and then we would set in our direction either counterclockwise or clockwise, and that's important too. I'm going to leave it on the default counterclockwise, but I really didn't pay enough attention to that. I should have paid more attention to the direction, and it is important. Alright, then for the first 60 degrees I want to dwell, and you can drag this back and forth. Notice there's a dashed line here in this segment that tells us that segment is active. I'm going to move this out of the way or maybe close it down. For my segment number 1, so I'm in segment number 1, I want that to end at 60 degrees, so I can type in exactly, and I'll click calculate down here, and we'll see that it moves that to 60 degrees. Okay, I'm going to click in the segment after that, and I'm going to say add another segment after this one, and then I'll click back into this segment to make it active, so segment number 2 is active. I want segment number 2 to go another 60 degrees or end at 120 degrees. Put in 120 and I'll calculate. We'll see that it moves it to 120, and then I'm going to tell it that I want it to lift a distance of 25 millimeters, and when I do calculate, now we'll see this is our curve for the lift, and for the acceleration curve we put in harmonic motion. Notice we have a choice of different motion laws that we can select, or we can import our own motion law. And then I want to go another 120 degrees, make this segment active. I'll add after, and then I want this one to go from 120 to 240. I want it to dwell at that 25 millimeters. So I'll type in 25 for the height for segment number 3. I'll do calculate, and then I'll come over, make this segment active, and then add a segment after this one, and then between 240 and 300 I want it to drop back down to 0, and then in my final segment, if I go to my next segment, I want it to dwell back at 0 lift. Notice there are a lot of different parameters for calculation if you get involved into the mathematics. I'm just going to go ahead and accept this and create the first cam. And I've set up a project so it's going to put it in a certain location. If we double click on this, we can give it a name. I'm going to call this cylindrical cam top. Click someplace on the screen and I will save the assembly. Let's make this one a different color so that we can keep track of what's what. I'm going to change this one to a red, and then we'll create another cam. So I'll do cylindrical cam again, and I'll leave everything set the same, but this time I'm going to set it on upper. Now we're going to move these, we're going to reverse these, and that's why I renamed that earlier one as top. I'm going to name this one bottom once I get done, because we're not doing the slot like this, we're doing actually this side and this side. I'll say okay, but I'm going to double click on here and I'm going to call this one bottom, and I'll click someplace on the screen. I'm going to make this one green, so I'll select it, come up here and go to the colors, and I'll set that to some green color. Alright, I want to make sure that this cam is at the origin, so I'm going to right click on it first and I'm going to make sure that it isn't grounded, okay, so it can be moved anywhere on the screen. Then I'm going to go to the Assemble tab, and underneath the Productivity Tools I'm going to select Ground and Root, and then I want to ground this component at the origin, so I'll select that component and I'll say OK, and then I'm going to mate the axis of this cam to the axis of this cam. Then I'm going to constrain, so I'll expand the origin folders and I'll put it on flush, and I'll select, let's do the YZ, so I'll do the YZ to the YZ flush between these two cams. Now if I drag this one still moves, so what we want to end up with is this one 20 millimeters below that one, so we want a 20 millimeter distance from here to here. Now I'm going to do another constraint, and this time I'm going to select the XY plane and I'm going to put on flush and the XY plane of the second cam. Okay, our follower was 35 millimeters, so that's what it put in here, was that 35 millimeter distance in here. I want to go minus 35, and that puts it down. Before I continue on, let's look at this in a little more detail. Notice that there is a bit of difference between here and here. The shape of the fall and the rise is slightly different, and that's why you don't see a perfect match up between there, is because of the shape of the fall and the rise, and we'll show you why that occurs here in a few minutes. It's because the follower is continuously, the tangent point between the follower and the curve is continuously variable, and it rides up one side of the follower on one side of the cam. We'll see all that in a minute. I moved it down 35 millimeters. I want to move it down another 20 millimeters, so that'll give me a 20 millimeter distance between here and here. I'll say OK to that. Now if I try dragging these two cams, nothing moves, everything is in position. All right, I'm going to go ahead and save this, and then I'm going to start a new metric part file. So I'll do a standard millimeter part. I'll go ahead and save this, and I'm going to call this Derived Cylindrical Cam. I'll go to the Manage tab and I'm going to select Derive, and then I will select the assembly that we just made. When I bring that in, I'm given a choice of how I can bring in those two parts. I can bring those in as a single solid body. I don't want that. I could bring that as a solid body but keep the seams between those two. I don't want that. I could bring it in, maintain each solid body. I do want that. Or I could bring it in as surface body. We'll leave it on this default and we'll say OK to that. Alright, now what I really want is the intersection between these two bodies, and so I'm going to go to the 3D model tab and I'm going to do combine, and I will select the first component, and this screen looks a little bit different in older versions of Inventor, but the process is basically the same. And I will select the second part as my tool body, and then I'm going to not go check keep tool bodies. The only thing I want to keep is the intersection where those two bodies intersect each other. So I'll select intersect and I'll say OK to that. So there is my cam. I might change the color of that to some other color, and when I changed the color it didn't remove the old color, so I'll come up here and I'll select on this clear, the beach ball with the X, and I want to clear any color overrides on that body. I'll say OK to that, and sometimes you have to do it twice, so I'll do it a second time, and let's check the bottom. Alright, so now I have this cam the color I want. If I look at this from this view, so we see the rise and the fall. Notice the rise and the fall are slightly different. So it's falling on one side, rising on the other side. That sets up the cam itself, so let's look at how to make the rest of the geometry to tie this all together. You may want to screen capture this image so that you can refer to it as I go through and I create the sketch and add the dimensions. So go ahead and take your screen capture. So this is the sketch for the body of the part. I also have to build this web in between here. And I've tried several different ways of building that, and I'll show you the way that I got to work the most efficiently, but you may have a better way of getting that to work. Now let me turn off the visibility of the body for a minute so that we can see the sketch. So for the sketch by itself, we're going to create this geometry, 9-degree angle between the center line and this line. These two lines are parallel, so let's look at setting all of this up. I thought about creating a patch across here, but when I do the patch, even if I put it on tangent, there's a lot of waviness. I don't know if you can make that out, but there's some curve going across here, which I don't really want. And if I put it on tangent, it's not right at all. So rather than do the patch like that, I'm going to do thicken offset, and I'm going to put my output on surface. So I have it set to surface. I'm going to select this face, and I see that it's going above the part. I want to go 2.5 millimeters, and sometimes I'll make it a large number so I can see which direction it's going, and then I'll flip that to go inside of the part. All right, then I need to extend this surface in so that it intersects the portion of the geometry tree that goes inside here. So I'm going to then do extend, and I'll extend that a distance of say 36. We'll come back and check this later on to make sure that we've gone far enough and we haven't gone too far. I'm going to do the same thing on the bottom. Now I tried offsetting this surface, but it really became slow, so it's just easiest, most efficient to do the same thing on the bottom. So I'll do thicken offset, make sure it's on surface output. I'll select this 2.5, but I want it to go up inside the part this time, and the part gets bigger as it comes down, so we don't need to extend that as far. So I'll go ahead and do extend, and for this one I'm going to extend 32. We'll look at those numbers later on. I'm going to go to the top view on a view cube, and then I'll start a new sketch on the XZ plane. I'll hit F7 for slice graphics, and then I'm going to draw a line someplace out here in space, and then I'll do coincident from this line, not the midpoint of the line, somewhere on this line to the origin. I will dimension the distance from the origin down to this point as 65, and I will dimension from the bottom of this line up to the top of this line, and for that distance I'll go 252. So if you made a screen capture earlier following along with what I'm doing, I will change this line to a center line, a center object line, and then I will draw a line from here over to about to here and up to here. I will dimension the distance from this line to the center line. That diametral dimension is 175. I will then draw a line from here over to here, back to here, and back to there. Now make sure that these two lines are horizontal and these two lines are vertical. Change this one to construction, and then I will dimension that diametral dimension from here to the center line. That distance is 222. The height of this line is 25. I'll then draw a line coming over horizontally towards the center, and then I will go up vertically. The diametral dimension from this line to the center line is 165. I'll come up and work on some of the geometry at the top now. So I'll draw a line over horizontally, and I'll go ahead and dimension from this point to the center line. That distance is 90. I will draw a line going down vertically from that point, and then over and down, back over. And I didn't get this line vertical, so I need to make sure that I have that line vertical. Depending on your coordinate system, it may be horizontal instead of vertical. We're just looking at it with it oriented vertically. I'm going to finish and save this, and then I'll go back to editing my sketch. Don't suspend the time between saves by too long. I'll hit F7 again, and I'll dimension the diameter between this line and the center line, and that one was supposed to be the 90, so I'll go ahead and just put it in, and then I'll double click on this dimension and I'll change that to 130.2. You should have been hollering at me, telling me you should have told me that was the wrong dimension when I made it earlier. And I'll make this one not the 90, and then I will dimension the distance from here down to the bottom of the part, and I'll do that as 170, and then from this line down to the bottom of the part, that distance is 191. I can connect together this point and this point. We could either put our angle dimension on this angle or on the side out here. I'll go ahead and put it in now. So I'm going to dimension from here to here as 9 degrees. Now if you click on the tolerance, you could set that to be 0 decimal places, so there's less clutter on the screen with only the 9 instead of 9.0. And I was expecting that that line to turn dark. It didn't, and I see that the height from here down isn't defined yet, but as we define our other geometry, that should fall into place. So then I'll dimension, or I'll draw a line from here over to here, come down and over, about like that. I'll dimension the diametral dimension from here over to here as 170. I'll dimension from here to here as 180. And then I'll dimension from this line down to the bottom of the part. That distance is 163, and I will put in the short vertical line, and then I will come down to that location, and now I'll make these two lines parallel to each other. So I'll do parallel. This line is parallel to this line, and that line didn't stay vertical, so I'll put a vertical constraint on that line, and now it turns dark. So then I need to determine why this line is no longer constrained, so I'm missing one dimension. If I drag this line, I see that the length of this line isn't defined and the length of this line isn't defined. The design intent was for this to be vertical from here down, and so I'm going to add a construction line in here, and I'll change that to construction. Now I could just put a coincident between here and this line, but it will help me in the future see where that was supposed to be by putting the construction line in here, just like I put the construction line down here. Now we see that everything is fully defined, and I'm going to finish sketch and turn off for a minute the dimension visibility. And so earlier we extended these two surfaces right here, and I just needed to make sure that those surfaces would intersect this line right here, and actually they have to intersect it as it revolves around here and it comes up higher on the angle. With the dimensions hidden for clarity, we can see that this is the area right in here that we want to revolve. So I went ahead and revolved that. I'll hide the sketch, and then we need to solidify the area in between these two surfaces to create the webbing between the conical portion of the part and the cam. So then I'll do sculpt. I'll select this surface, and so we just needed to make sure that it intersected the cone all the way around, even as it came up here higher. So that's what we did the offset for earlier, and then the extend, and then I'll select that face or that surface, and so in between those two surfaces it's going to solidify. I'll then put some fillets and chamfers on here, so I'm going to do a fillet on that edge, radius 5. I'll do some additional fillets. I'm going to fillet this edge, and let's change that to 1.5. And I'll select this edge down here, this edge right here, and this edge right here, and this edge right here. I'll say okay to that. And then going to put some chamfers on here. So I'll do a chamfer, and this one is a large chamfer, 5 millimeters. And then I'm going to do some 0.5 millimeter chamfers just to break some sharp edges. So here and here, I'll break those two sharp edges, here and here, and also up here. I might break the sharp edges of the cam as well. Then you could paint the faces that you want painted, or I'm going to put a rust color on that. So I'll go to the properties of that face, and I'm going to find a rust color or texture. I'm going to change that to rusted, and that pattern might be a little bit too big, so if I pick that up with the eyedropper, I can drag this, make that bigger or smaller, or I can rotate it. You get the appearance that I want, and then I can drop that appearance onto other features or other faces. I may want to drop it on that face. If I want to put it over on those smaller fillets, if I hold down the control key, I can select the feature from the browser, and I may want to do the same thing on the other side. Up with the eyedropper, I'm going to select this face, and let me check the bottom of this, and this face, and get one more face in here, do it on this face. So that completes my cam. Next we'll see how to put this into dynamic simulation. I started a new assembly file, and I will place the follower assembly, and I'll place that grounded at origin. I'll put a link in the description for the remaining parts for this assembly. I have this pusher ram assembly as flexible. If I try to drag the follower, I see that it doesn't move, so I have it set as flexible. So I also need to set the main assembly as flexible. And now when I drag the follower, it will move up and down. Now I'm going to give you step files, so you will have to constrain all of the components appropriately based on their location in the step file. I'll then do place, and I will place our cam into the assembly, and I'm going to do constrain, and I will do insert, and I'm going to select this circle on top of this feature, and I'll select this circle inside the cam, say OK to that. And so if we try to drag this, we have 1 degree of freedom rotation as we expect, and then on this one we have 1 degree of freedom translation. Now I put the rollers in here as fixed. In reality, they would also rotate, but to simplify this, I will ignore that degree of freedom. If we go into dynamic simulation, then we would expect to see 1 prismatic joint, and that's the up and down motion of this piston, and then 1 revolution joint, that's for the cam. I'll go back to the assembly environment. Now I may be able to get a rotational translation constraint to work with this. We'll try. Sometimes it will work and sometimes it won't. I have a tiny little bit of clearance between here and here. So the thickness of the cam is 20 millimeters. I have the distance between these rollers as 20.1 or something close to that. And then I'm going to do a constraint, and I'll attempt to put a transitional constraint, and I will select this face first, and then I'll select this face. And it looks like it moved it to the wrong place, but I'll go ahead and say OK and see if it moves it to the correct location. And it moved it down into the correct location now. Then I will try dragging this. And so as I drag the cam, we see that the follower rises up and follows the cam. And then as I go back down, the follower goes down the cam. Now what we may want to do is check to see on this roller if there is any interference at any position along this cam. As I said, I put a little bit of clearance in between there. You can do that on the inspection tab using analyze interference, put the cam in different locations. Now if the interference is insignificant, tiny number going out to exponential notation to a really small decimal, then you can probably ignore it. The transitional constraint is not automatically converted to a dynamic simulation joint, and so we're going to need to add additional joints in the dynamic simulation environment. If we just want to run this in the assembly environment, we could put an angle constraint between the cam and the origin of the assembly and drive that angle constraint to cause this to rotate. Let's go ahead and do that. So I'll do a new constraint, and I'm going to put it on an angle constraint, and I have it set to explicit reference vector angle, and I'll select one of the planes in the assembly, and I think the YZ plane would be appropriate, and then I will select one of the planes in the cam, and again I think the YZ plane would be appropriate, and then I'll select the rotation axis, so I'll select the axis of the cylinder, and I'll say OK to that. And in this case it gives me an error. I'm going to go ahead and accept that, and I'm going to suppress the transitional constraint, and then I'll move this down to where it's close to being in position, and then I'm going to unsuppress that transitional constraint. So I'll do unsuppress, and so it moved it down into position, and then I'm going to drive the angle constraint. So I like to name this as drive this. So I renamed that angle constraint, and then I'll do that. I'll right click on it and I will select drive, and I'm going to go, let's say 7200 degrees, and I'm going to expand this, and I'll tell it to do as the total number of steps, or I'll just do every 1 degree, and I'll go ahead and play this, and hopefully it plays. I may want to speed that up, and so if I increase the increments, let's say go every 10 degrees, and I'll continue playing that. And so we see that motion. If I want that to go even faster, put this up to 100. If I play it too fast, it may give me an error, as it just did. So that is in the assembly environment. Now I tried to put all 4 of them in here with a transitional constraint, and I couldn't get it to work. You may or may not be able to get it to work. Before I go into dynamic simulation, I need to suppress this constraint. So I'll suppress that, and then I'll go to environments, dynamic simulation, and then I'm going to put a 3D contact between this part and this part. So I'll do insert joint, I'll do a 3D contact, and I'm going to select this part, and I'll select this part. I'm going to put a force on here to hold the follower against the cam. So I'll do a force at that center of that circle pointing down, so I need to flip that direction, and let's do that, let's say as 1,000 newtons. Now we saw with the 3D contact before setting the stiffness, so I'm going to go to that 3D contact, and I'm going to edit the properties of the 3D contact, and I want to increase that stiffness quite a bit. These parts would probably be case hardened, for certainly the roller would be case hardened, and perhaps the cam would be case hardened. I'm going to increase this value. I'm going to put 2 more zeros in here, and then I'm going to increase the dampening. I'm going to put that as 100. So I don't want the materials to bounce when they come in contact with each other. I could put a friction value in here, but for now I'm going to leave that friction value off so that it calculates faster. And then I'll find the revolution joint, and I'll go to the properties of the revolution joint, and 1 degree of freedom revolution. I'm going to enable and impose motion. I'll do a constant value, and this cam operates at 150 RPM, so I can put in RPMs, and when I hit the tab key, it'll convert that to degrees per second. But if I go back and edit it, we still see the RPMs that we started with. And also under the simulation settings, if you expand this dialog box, somewhere there's an option where you can tell it input angular velocity in revolutions per minute, or RPM. And then I'll go ahead and play this. Now initially it has to do calculations, so it's maybe a little bit slow on the calculations. In this case we're doing 100 calculations. We may want to increase that number of calculations. Once the calculations are complete, you can rewind and play it back. In this case we're doing 100 calculations. It created 100 slides to represent the motion. If we would like to see that motion occur more quickly, then we could rewind, change this, instead of showing every slide, to show, say, every 10th slide or every 20th. I'll put it on every 10th slide, and I'll play it again. Now if we want this to really play smooth, we need to publish this to Studio, where we can tell it to run. To make this easier to see, I'm going to turn off the visibility of some of the other components. And so I'll shift right mouse button and select part priority, and then I will turn off the visibility of this component, and it may give me some kind of warning. I'll just say okay to that, and I'll turn off the visibility of this component, and I'll turn off the visibility of this component. So now I can see the 2 followers, and I will play this, and we can watch this as it transitions across the cam. So right now we're in the lower dwell area. We'll rise up one side to the upper dwell area and then drop down the other side. So I'll go ahead and play it, and I may need to slow that down so that we can watch that a little bit more carefully. Instead of every 10th slide, I'll show every slide. I'm going to stop it right here. So notice the tangent point on this cam is about right in here at, say, the 2 o'clock position, and then here it's about the 7 o'clock position. So that tangent location between the cams and the follower is continuously variable. It's in dwell at the upper lift, and then it begins to fall. dwell for 120 degrees, lift for 60 degrees, dwell for 120 degrees, and then fall for 60 degrees.